have in numbers 7 and 8, it says to write each expression as a sum and or difference of logarithms. Express powers as factors, or in this case as coefficients. And for number 7, we have the base 3 logarithm of x squared times the square root of y plus 4 all over the fourth root of the cube of the quantity of z plus 2. And in the case of 8, we have the base 5 logarithm of the ratio 7t squared u to the third all over v to the fifth times z. Now, for number 7, rewriting the radicals as non-integer exponents. We have x squared times y plus 4 raised to the 1/2 all over z plus 2 quantity raised to the 3/4. And again, we have with our terms, once we expand, any attachment that is at the top will result as a positive logarithmic term. Anything that is in the denominator will result as a negative. So we have with our first expression or factor at the top, we have x squared. So the base 3 logarithm of x squared. And we have next, we can say we have plus the base 3 logarithm of the quantity of y plus 4 raised to the 1/2. And with z plus 2 raised to the 3/4. At the bottom, we have minus the base 3 logarithm of the quantity of z plus 2 raised to the 3/4. And looking at taking what we have, rewriting the exponents as coefficients. So we're going to have, upon moving, we're going to have in the expanded form, we come out to 2 times the base 3 logarithm of x. And we have plus 1/2 of the base 3 logarithm of the quantity of y plus 4. And we have minus 3/4 of the base 3 logarithm of the quantity of z plus 2. And that will be the final answer in the case problem number 7. And for what we have in number 8, if we write in expanded form, so we will have the base 5 logarithm of 7, then we have plus the base 5 logarithm of t squared, plus the base 5 logarithm of u to the 5th. And we have next with the v to the 5th and z at the bottom, we'll have minus base 5 logarithm v to the 5th. And we have minus the base 5 logarithm of z. And so we have in the follow through. Now, first term in exact form, this is already in simplified form since neither 7 is neither a multiple nor an integer power of 5. And as for base 5 logarithm of t squared, so the exponent becomes a coefficient. So we have plus 2 times the base 5 logarithm of t. And we have next, we have plus what's going to be 5 times the base 5 logarithm of u. And we have minus, we have what's going to be 5 times the base 5 logarithm of v. And again, we have minus the base 5 logarithm of z. And this will be the result, the final result for what we have in number 8. For numbers 9 and 10, we're looking at going from expanding to compressing as a single logarithmic term. And for number 9, we have 3 times the base 5 logarithm of w, minus 2 times the base 5 logarithm of x, plus 6 times the base 5 logarithm of the quantity of y minus 4, minus 3 times the base 5 logarithm of z. And for number 10, we have 2 times the base 3 logarithm of u, plus 3 times the base 3 logarithm of the quantity of v minus 4. And we have minus 3 times the base 3 logarithm of the square root of w to the 4th minus x cubed. All right, so looking at making into a single expression. So any coefficients we have out to the front, I can make into exponents. And for the terms that we have in problem 9, so we have upon expanding, so we're going to have the base 5 logarithm of w to the third. And we have minus the base 5 logarithm of x squared. And we have plus the base 5 logarithm of the quantity of y minus 4 raised to the 6th. And we have minus the base 5 logarithm of z to the third. Okay. So we have the coefficients all converted into exponents and making out into a single term. Again, we have base 5 logarithm, and the attachments of the positive base 5 logarithmic terms will go at the top. Those that are negative will go to the bottom. Okay, so we have w to the third. This will go to the top. And from minus the base 5 logarithm of x squared goes to the bottom. Next term we had to be a positive, so y minus 4 to the 6th will go to the top. And with the last term being a negative, z cubed goes to the bottom. Okay, and so this is one way that the final result can be expressed in the case of number 9. Now, for number 10, okay, I rewrote the square root of w to the fourth minus x cubed as a non-integer exponent, where we have w to the fourth minus x cubed quantity to the 1/2. Now, still working with what we have with the leading coefficients, writing as exponents. And we're going to have in the conversion, so we had the base 3 logarithm of u squared. And we have plus the base 3 logarithm of v minus 4, which would be to the third. And we have minus the base 3 logarithm. And we have w to the fourth minus x cubed. Now we have to the 1/2. But again, we'll be taking this expression and raising to the third. Okay, so just momentarily putting the combining of the terms on hold. Okay, so we have base 3 logarithm of u squared again. We have plus the base 3 logarithm of v minus 4 quantity to the third. And now we have in the rewrite, we have the last term. We're going to have w to the fourth minus x cubed quantity, and to the 1/2 and to the third, multiplying the exponents. We have this difference to be raised to the 3/2 degree. So we can go ahead and combine our terms. So we have a base 3 logarithm, and with the first two terms positive, the attachments will go in the numerator. So we have u squared times the quantity of v minus 4 to the third, and the last term negative, we're going to have w to the fourth minus x cubed raised to the 3/2 at the bottom. And this particular term is going to be the result for number 10. Okay, for numbers 11 through 13, it says to determine the value of x and to round each answer to the nearest 3 decimal places. Okay, so we have for this particular remaining group, okay, we have, first of all, we have 2 to the x is equal to 3, and we have x is only on one side of the equation, and I can convert 2 to the x in terms of x, so I can apply base 2 logarithms on both sides. So you have the base 2 logarithm of 2 to the x, so the base is 2, logarithmic and exponential will go out, and we have the x again is equal to the base 2 logarithm of 3, and I can use the change of base formula. I can say that x is going to be the natural or the base 10 logarithm of 3 over the natural or base 10 logarithm of 2. And so for what we have in the result, when taken to the nearest 3 decimal places, we have x at about 1.585. Now for number 12, we have e to the x minus 2 is equal to 14, and x minus 2, okay, we have on the left-hand side the equation, and I can eliminate the e by taking the natural logarithm on both sides. So we have left-hand side natural logarithm of e to the x minus 2. That becomes x minus 2. Now for the natural logarithm of 14, we have this waiting for the 2. Okay, and once we isolate x, again we have x equal to the natural logarithm of 14 plus 2. And for the natural logarithm of 14, okay, that is about 2.639. And if I add 2, we have to the nearest 3 decimal places, we have x at 4.639. And for the last problem, okay, we have x on both sides of the equation, and we have 10 to the 3x plus 1 is equal to 12 to the x minus 1. And now I can apply either natural or base 10 logarithms, and we'll go with base 10 logarithm. Again, just log, okay, that's just going to be base 10 logarithm. And this will take care of the exponential base 10. Okay, so we have, in this case, left-hand side will become 3x plus 1. The base 10 logarithm of 12 to the x minus 1. I can make the x minus 1 into a binomial coefficient. So we have 3x plus 1. And distributing on the right-hand side, we have x times the base 10 logarithm of 12 minus the base 10 logarithm of 12. And looking at gathering what we have in the expressions. So I'm going to take x times the base 10 logarithm of 12 and join with 3x. And simultaneously, I can take away 1 and deduct from the negative of the base 10 logarithm of 12. And so looking at what we have now, so I have 3x minus x times the base 10 logarithm of 12 is equal to the negative of the base 10 logarithm of 12 minus 1, and factoring out x. So we have x times the quantity of 3 minus the base 10 logarithm of 12. And again, we have equal to the negative of the base 10 logarithm of 12 minus 1. And we have in isolating x, if I divide out, say I have minus the base 10 logarithm of 12 minus 1 all over 3 minus the base 10 logarithm of 12. And just putting this in calculator terms, so we have the quantity of the negative of the base 10 logarithm of 12 minus 1. And we have all over, and we have the quantity, and we have a 3 minus the base 10 logarithm of 12. So close out for 12, close out for the difference in the denominator. And for what we have approximately for x, minus 1.082.